Okay, so here we are with the fourth and final lesson in this unit on combinations.
Just a small unit on combinations.
Yeah, just a small unit. And really what we're talking about now is problem solving with permutations and combinations. So let's mix some stuff up here for you.
Yeah.
And let's help you decide what's a permutation
and
what's
how
a
to
combination.
Distinguish.
Yeah.
So what we'd like you to do first, so so pause this after we give you this set of instructions. Identify whether each of the following problems represents a permutation, so order matters in time or space, or a combination where order doesn't matter, only the selection matters. So run through and put like a P or a C next to each of these questions and ask yourself, would order matter? Would you care about the order if you were in this position? And then once you've determined that, then you can come back in and watch with us and we can solve these.
Okay. Yeah. So we'll start with, basically this is just a whole bunch of little examples, and that's what we're going to run through today, just to give you some of this practice. So how many 5-digit numbers can be formed using each of the digits 1, 2, 3, and 4? Permutation or combination?
Well, if it's a 5-digit number, and say it was a passcode or a phone number, order would matter, so it's a permutation.
It is a permutation.
Yep. And I want a 5-digit number using each of these 5 digits once.
Yep.
So it's 5p5 or 5 factorial. Okay, so we have 120 different ways.
Cheaters.
We gave away the next, but don't worry, you had already gone through and figured out that the second one was a permutation. So in how many ways can 6 runners finish a race? Well, it matters to you which order you finish that race in, probably. So that's a permutation.
Yep. So that's definitely a permutation.
Yep.
And of course, how many ways can 6 runners finish a race? Well, we get 6 options for first. We got 5 options for second. 4 options for third, and so on and so forth.
6 spots, 6 factorial.
720 different ways.
You got her.
3 of 5 people are chosen to go on a trip. How many ways can they be chosen?
They haven't said anything about shotgun here, so I think order doesn't matter.
Order does not matter.
No, I just want to go on that trip.
So is this permutation or combination?
Combination.
It's a combination.
No.
And if I've got 5 people to choose from, and I'm going to choose 3 of them.
5 choose 3.
There's 10 different combinations of people.
Yep.
Okay. A bridge hand consists of 13 of 52 cards. How many different bridge hands are there? Now, even for people that don't play bridge, really, whenever you're playing cards, does the order of the cards that are in your hand matter?
In most cases, no.
In most cases, in almost all cases, no.
Yeah, yeah.
Is this a permutation or a combination?
So if order doesn't matter, then it's a combination.
That's right. And if I have 52 cards to choose from,
and
I'm
choose 13?
choosing 13, now this is a huge number. 6.35 times 10 to the 11th different hands. So there's tons of hands.
That's why bridge is so exciting.
Oh, I've never played.
No. Neither have I.
All right, so you want to order a medium-sized 3-topping pizza.
I do.
With no gluten in the crust.
There you go.
There are 8 toppings available. How many different pizzas can you order if you choose 3 different toppings? Now, does the order of those toppings matter?
I think that the argumentative among us could say, like, you have to have the cheese on top or whatever. But let's say that in general, you spread them around, they get all mixed around.
Yeah.
It doesn't matter what order they go on, only that you're eating them.
Yeah. So we're going to say
no.
That order doesn't
matter. Combination.
The pizza purists might say pepperoni first, then a vegetable, then cheese. But we're going to say no. This is a combination.
Yeah.
Topping order does not matter.
No.
So if I have 8 toppings to choose from and I want 3, 8 choose 3 is 56 different pizzas. All right, so how many arrangements of the word field are possible?
This one's a bit of a giveaway, Mr. Jackson. You'll notice that often if you see the word choose or select, then you're dealing with combinations. And if you see arrangement or order, then you're like, oh, that's probably a permutation. So we're arranging those letters.
Yes, by virtue of the fact that this question has the word arrangements in it, we're talking about a permutation.
Yep.
And of course, there's 5 original letters.
Yep. And they're all distinguishable.
5 factorial ways.
5 factorial. Yep.
All right. 10 people shake hands with each other. How many handshakes are possible if no pairs shake hands twice? All right, so in a handshake...
Does it matter what order you reach out?
No.
Not really.
I don't think so.
No.
If I shake your hand, I think that's pretty much the same as you shaking as you shaking my hand.
I think so.
I think that basically a handshake is really just a combination.
Two people coming together.
Yeah. And so if we've got 10 people that are all shaking hands, we're basically taking those 10 people and we're saying, hey, how many combinations of 2 people can I make?
How many different pairs can I make
Exactly.
out of a group of 10?
This is a combination, and we would say here that 10 choose 2 is 45 different handshakes.
You got it.
That's a little bit trickier.
It's a little bit trickier. It's hard to think about it. Some people try to set it up like they say the first person could do 9 handshakes, and then the second person who's already shaken the hand of the first person now only has 8 handshakes, and you can sort of work your way down. You can use logic and make a systematic trial and error kind of thing here, but that's not efficient. If you think about it as I have a pile of 10 people, and I want to know how many different 2-person pairs can I pull out of that pile, that's all you're doing.
That's all you're doing.
Yeah.
A committee of 4 people is to be chosen from a group of 12. How many committees can be formed? Again, key word here, and it's a dead giveaway.
Chosen.
Or, you can talk about chosen. You can also talk about committee. If you're forming a committee of people or a group of people, you're talking about order not being important.
Well, especially because they haven't given us any role. Like, I've been told like the first person chosen will be the treasurer or something like that.
Then order's important. But here it's just a committee. So this is a combination.
Yeah.
And we have 12 people. We're choosing 4 of them. 495 different committees.
There you go.
A committee consisting of president, vice president, treasurer, and secretary is to be chosen from a group of 12. Now, all of a sudden, we've included the word committee.
And we've included the word chosen.
But we have positions that are now important.
Yeah.
So positions being important, it's like finishing a race in first, second, third.
I would care.
This is a permutation.
Yeah.
Okay, so don't let these keywords throw you off. It's not a hard and fast rule.
No.
As soon as we mention positions, what we're getting at is, this is a permutation. Order is important. There's 12 P4 ways of selecting this committee with these positions.
And notice there's a significantly larger number of ways when order matters, right? Same thing, 12C4, 12P4. The only difference is for the permutations we're ordering them, it's 11,880 as opposed to 495. So,
In how many ways can 10 people be divided into 2 teams of 5 people each?
This conceptually is a challenging one.
Yep.
In terms of permutations and combinations, not so much, but in terms of the solution, a little bit more. If I just want a team of 5, then, I'm just going to say you 5 over here, you 5 over here. Order doesn't matter, right? So it's a combination, but at the same time, we actually have to make a choice in 2 stages. We have to take those 10 people and say, all right, I'm going to choose you 5 to be on the first team. So basically you have a pile of 10, and you want to choose 5 from that pile of 10, and now they're out. And now you look, and now you have a new pile. It's a smaller pile of 5. And now you want to choose, I guess, all 5 from that pile of 5. But because you're doing this twice, you've got like 2 stages you're making decisions on.
So this is a combination because we're just making teams. And really, we'd have 10 choose 5 for the first group, and then 5 choose 5 for the second group, which is 252 ways. So those are kind of a lot of general examples and ideas, all based around this notion of either permutations or combinations. Let's do the same thing, but let's work from a very specific point of view. Let's look at hands of cards. Okay? And so in this example, we're going to deal 5 cards from a deck of 52.
So assume all of these are 5-card hands.
So same example. Are these permutations? Are these combinations? How do you solve them?
All right.
How many different hands can be dealt? Permutation, combination.
Well, I just want to choose 5 or select 5 out of the 52. So order doesn't matter.
Nope.
So it's a combination.
It is a combination. And this would be 52, choose 5. There are 2,598,960 different 5-card hands.
It's a lot of different 5-card
hands.
Yep.
How many hands then will contain all face cards?
All right. So for A, we had a pile of 52 cards and we were choosing 5. But now, if we want all face cards, we've significantly reduced the pile size.
Exactly.
So we have to think, well, how many face cards are there? There's 4 jacks, there's 4 queens, there's 4 kings. So there are only 12 face cards in the deck. And so if I want to choose 5 from those 12, I've reduced the pile size to 12, but I still want to take 5 of them.
So again, this is still a combination.
Yep.
Right? So there's 12 face cards in a deck. 12 choose the 5 is only 792 different hands that contain all face cards.
Yep. And now when you start thinking about this, of the magnitude of hands that could be dealt, 2.5 million, versus how many hands are actually winning hands, this sort of starts to set you up in thinking about what our next unit is, which is probability.
Yeah.
And we're going to do a lot
of probability.
Yeah.
Because poker hands are, of course, 5-card hands, and there's only 2.5 million of them. Well, really 2.6 million.
Yeah.
There's 2.6 million different poker hands. There's only 4 royal flushes.
Yeah.
So the probability of getting one is really low. And so this kind of example is going to set you up to say, oh, this is maybe where we can use permutations and combinations in probability. Okay.
Yeah.
How many hands contain no face cards?
All right. So we're still, because we're dealing 5 cards from a deck of 52, essentially every question relating to this setup, they're all going to be combinations, right? Unless they introduce a different element. So this one's also a combination. If we want to know how many hands contain no face cards, okay, well, then, you know, we got to think about this a little bit, because we've got a deck of 52. We know that 12 of them are face cards. And if we want to create hands where there aren't any face cards, then we can just throw the face cards right out of that pile. So we're going to take 52, we'll subtract out the 12. There are 40 cards that aren't face cards, and those are the only ones that are desirable. So we want to take those 40 and we want to choose 5 from that 40, because we wanted to kick out the face cards. Yeah.
So we got 40, and we're going to select 5 of them.
Yeah.
So we get 658,008.
There you go.
All right. How many hands will contain only spades or clubs? So no red cards at all. So how many hands will... Well,
so there are we implying all 5 are spades or all 5 are clubs?
No. We're saying all 5 are spades or clubs.
Okay. See, I would interpret that as containing only spades or only clubs.
Or only clubs.
And now, if you ever encounter a question like this on a test,
this would be a time to ask.
Then you would want to ask for clarification.
All right. Well, let's see what we thought when we made the lesson.
Yeah.
Yeah. So it's basically 26, because there's 13 spades, there's 13 clubs. And so what we get is that those 13, there's now, our pile is only 26 cards.
Yep.
Right? So it's black, it's all the black cards. There's 26 of them. We're choosing 5. So we have 65,780.
Yeah.
And of course, the difference between only spades or only clubs would be a little bit different.
It would be 13 choose 5 plus 13 choose 5. So it would be a different solution altogether. Yeah.
So how many hands will contain only hearts? Well, again, this follows right along from example D. There's only 13 hearts in a deck. We're choosing 5 of them. We get 1,287 different hands with only hearts.
Yep.
How many hands will contain at least 1 queen? Okay, now we're starting to get into at least.
At least or at most. You know, you have cases.
Yeah, we're going to have cases. Sometimes it might be appropriate to use an indirect method.
Yeah.
Okay.
Because if you want at least 1 queen, you could have 1 queen, 2 queens, 3 queens, or 4 queens.
Yes.
In your 5-card hand.
Exactly. So let's use an indirect method.
Because the only undesirable case
is no queens, right?
Yeah.
So basically, the case where we've got at least 1 queen is equal to all of the different combinations minus the ones where we have no queen.
Yeah.
Okay. And so no queen would be, okay, well, if there's 52 cards in a deck and we throw out the 4 queens,
see you later.
48 choose 5 is 1,712,304 different hands.
Yeah.
Right? We've already solved for all the different combinations of hands. So now we've got, so now we've got 2,598,960 minus the case where we have no queens. And what we end up with is 886,656 possible hands with at least 1 queen. And the last couple examples here, how many contain exactly 2 4s?
So here's the thing to think about. We definitely want there to be 2 4s, and then we want the other 3 cards to be not 4s.
Yep. So we don't want to accidentally include more cards.
Include a third or a fourth 4 or something like that.
So we're going to set up our 4 4s, and we're going to say 4 choose 2. But we're also going to set up the remainder of our cards that aren't 4s, and there's 48 of those. And from there, we're going to choose 3.
Yeah.
We still want this denominator to be 5. Like, we still want this bottom set. If we draw a horizontal line across here, we still want this to add up to 5.
5 cards, yeah.
And we still want this top line to add up to 52.
Yeah. Because essentially what you're doing is you're taking the 52 cards and you're breaking them into 2 piles.
Yeah.
A pile of 4s and a pile of non-4s.
Yeah.
And then you're going to take 2 from this pile and then 3 from that pile. So in order to set this up and multiply them, we can't have any overlap.
Exactly.
Right. So what Mr. Jackson is saying there, so the n's in the n choose r, the 2 n's together should add to your total n, which was 52.
Yep.
And the 2 little r's together should add to your total r, which was 5. So when you think about this, think about breaking it into piles.
Mm-hmm.
And then once you've broken it into piles, you're going to take some of these and some of those.
Mm-hmm.
And that's when you can multiply them together. Yeah.
This is 6 times 17,296, which is 103,776. Hands with exactly 2 4s.
Exactly 2 4s.
That's a lot. That's surprising.
Good.
Okay, how many will contain a jack or a king?
So exactly 1 jack, not 2 or 3 or 4, or exactly 1 king.
Mm-hmm.
And if you have the jack, then not the kings.
Mm-hmm.
Okay, what do we got, Mr. Jackson?
All right, so here we go. This is one where we're going to use the additive counting principle because we have an or.
Yep.
So we got 4 choose 1. So these are the jacks, exactly 1 jack.
Yep.
And here's 48 choose 4 because we want the rest of the cards to be not jacks.
Yep.
Plus, we're going to add that to the case of kings. We want exactly 1 king, 4 choose 1, and 48 choose 4.
Yep.
Right? So this is a jack or a king.
Yep.
And so what we get is, of course, 4 times 194,580, and we're multiplying by 2 because these are the exact same.
That. Yeah.
So 1,556,640 hands with a jack or a king.
Or a king.
How many will contain 2 jacks and 2 aces?
So we've got exactly 2 jacks, not 3 or 4, exactly 2 aces, not 3 or 4, and then a 5th card that's neither jack nor ace.
Yeah.
Right? So we've got 2 of jacks, 2 of the aces, and 1 of the other. So that's 44. Imagine we've, again, split the deck into 3 piles. 4 are jacks, 4 are aces, and then the 52 minus 4 minus 4. The other 44 are neither jacks nor aces. So once we've split it into 3 piles, then we're going to take 2 of these, 2 of those, and 1 of those. Okay, so 4 choose 2 times 4 choose 2 times 44 choose 1. 6 times 6 times 44 gives you 1,584 hands that have 2 jacks and 2 aces and then something else.
Mm-hmm. Okay. And that is it.